So I think we have two more classes, right? We have one on the 23rd, after today, one on the 23rd and one on the 30th, right? So if, on the 30th, if you have questions about anything, we can answer those, we can talk about those. Otherwise, we'll just do something. But we can have a review if you have questions on how to do anything. Okay? So this is chapter 9, and it's called, they call it hypothesis test. So it's about when you have some hypothesis, some statement, and you want to test it statistically. So you might say, I think that APU students prefer I don't know, prefer what? Taking the bus rather than, no, that probably isn't true. I think APU students would rather have international food at every meal or something like that. So you want to test it. You want to see whether it's really true or not. So you have some hypothesis and you want to test it. And that's what this is about. And the idea is that this is chapter 9, that we can use everything that we've learned before chapter 9 to test that kind of hypothesis. And especially what we can use is what we learned in chapter 8, and in particular in chapter 8, about intervals, confidence intervals. So you remember that we talked about confidence intervals last time. So that's what this is about. So why do we need to perform a hypothesis test? Reconsider the example about soft drink cans. Suppose we take a sample of 100 soft drink under investigation. We then find out that the mean of soda in these 100 cans is 11.89 ounces. So you might think, oh, I'm being cheated because they say that the soft drink cans have 12 ounces of soda in them, but we took a sample of 100 of them, and the average was only 11.89 ounces. The question is, can you claim that you've been cheated? What do you think? Suppose that they advertise that the cans contain 12 ounces, and then you take a sample of 100 cans, and you get the average for those 100 cans is this. What would you say? Can you go and say, can you sue them? Can you go to court and say, you're cheating us. You're falsely advertising, and we're paying for 12 ounces, but we're getting less. What do you think? Can you say that? Well, that's the question. Can you say that or not? Okay, so based on this result, we can state that on average, all such cans contain less. Notice this word, all. Right? Well, that's not really all. We didn't test all, right? We just tested 100. But we can we state that on average, all such cans contain less than 12 ounces of soda, and that the company is lying to the public? And they say, no, we can't do that, not until we perform a test of hypothesis can we make such an accusation. So what do they mean by this? What's the hypothesis here? What would we say the hypothesis is? Now there's two possible answers, but if you can give either one. What do you think the hypothesis is here? Hypothesis. What are we testing? What do we want to test? Anyone? That's correct. It's the amount of soda that the can contain. But usually in a hypothesis test, we want to state one opinion and then test that one. So if we want to state one opinion, how would we change what she said? So the hypothesis might be that it's less than what they said. Okay? Now that's what I would say also. But usually the way they state it is slightly differently. Or they say that it's 12 ounces. The hypothesis is that it is 12 ounces, or that it's 12 ounces or more, for example. Okay? And that's the hypothesis that we're testing. Okay? I would say, yeah, that we want to test the other one, but really the way they usually do it is they say they want to test this one. And it doesn't really matter that much, but that's the way it's always done. Okay? So we're going to test a hypothesis that what? That the average for all cans is 12 ounces or more. And we want to check whether that's true or whether it's false based on the evidence that we've collected. What evidence have we collected? What's that? The evidence is that the average of the sample is 11.89. So the question is, can we say that they were lying based on that evidence? So yeah, we'd want to say, yeah, they're lying, but there's a certain element of what here? Certain element of randomness here, right? When we collect a sample, there's some element of randomness, right? So just because our sample was 11.89 doesn't mean, we know that, there's some variability in the cans. And so we might have collected a sample, just a kind of slightly weird sample, that was less than that. That doesn't necessarily, just because we collected a kind of weird sample doesn't mean we can sue them, right? And make them pay damages. So we want to be more careful than that, right? That's the idea. Okay? So they say the difference between the 12 ounces, the required average amount for the population, and this, the observed average amount for the sample, may have occurred only because of sampling error. And we talked about sampling error somewhere in the past, right? What sampling error is. Assuming that no non-sampling errors have been committed. We also talked about that. Another sample of 100 cans may give this. Therefore, we perform what we call a test of hypothesis to find out how large the difference between 12 ounces and 11.8 ounces is. So is that like within one standard deviation, for example? Or what I want to say is 12 ounces within one standard deviation of this? If it is, then it's not so likely that that they have cheated us, right? If it's like 5 standard deviations from this, then it's pretty likely that they're cheating us. Okay? So we want to check in that way. We want to find out basically how many standard deviations 12 is from 11.89. Now you talked about that, you did that in chapter 8. We talked about how to get the standard deviation. Remember, how did we have to get the standard deviation in our last class? We wanted to use the standard deviation of the population, right? But we couldn't, right? So we had to estimate it with what? The standard deviation of our sample. Okay? So we're going to have to do that same kind of thing. We're going to use that same kind of idea, those same kinds of ideas to figure out how far this is from 12. If it's really far away in standard deviations, then I'll say that it's really unlikely that my sample could have been that far away from 12. So that means that 12 is just too far away, and I can reject their hypothesis, or reject their claim that the logic behind what we're going to do. Okay? So, what did they say? To investigate whether or not this difference has occurred as a result of chance alone. Now, if 11.89 ounces is the mean of all cans, and not just our 100 cans, then we don't need to make a test of hypothesis. Instead, we can immediately state that the mean amount of soda in all such cans is less than 12 ounces. Of course, if they're all cans are this, then all cans are less than 12 ounces. We perform a test of hypothesis only when we are making a decision about a population parameter based on the value of a sample statistic. So let's just say that one more time. What are we testing? What was the hypothesis? What did we say the hypothesis was? Let's say we had 3 people suggest, or 2 people suggest hypotheses, and then I sort of said, but they usually do it this other way. So what was the final way that we decided is going to be our hypothesis? Yeah, okay. That the amount of soda, but I want to throw in one extra word, that the amount of soda, the average amount of soda for all cans, okay, is what? Is 12 or more, okay? Okay, so, but the key word there is all. All, therefore, means I'm making a statement about what? About the population, about a population parameter. And then I'm going to test it with what? Not with the population parameter, because I don't have that. I'm going to test it with what? A sample. And remember, what we call something from a sample, we call it a statistic as opposed to a parameter. Okay, we call something a parameter when it comes from the population. We call it a statistic if it comes from the sample. So we're going to test something about a population parameter, a statement about a population parameter, with something from the sample, which we call a sample statistic. Okay, and that's always we always do it that way. Okay, when we do this chapter 9, when we do this so-called hypothesis testing. So let me say it again. We always test a statement about a population parameter with a sample statistic. Okay, but you'll see that. Let's just do it here. Okay, here's another example from a completely different thing. Okay, consider a non-statistical example. A person who has been indicted for committing a crime and is being tried in court based on available evidence. So there's that word evidence again. What was evidence in the last example about the soda cans? What? The mean of the sample, right? Okay, the evidence came from the sample, okay? Now we're using evidence in a kind of a different way, but it's sort of the same way actually. Based on evidence, the judge or the jury will make one of 2 possible decisions. The person is not guilty, or the person is guilty, right? So we can say there's a kind of hypothesis here that we're testing. What's the hypothesis that we're testing in this scenario? It's the one here I have. I'm sorry. It's the one, maybe this one. It could be either one, right? But I think this is the one we usually say it is. Okay, the person is not guilty. Okay? So we're going to test that based on what? Some evidence, right? So what happens? Who presents the evidence in this scenario? The state tries to collect evidence that the person is guilty, right? And they have to try and prove that the person is guilty based on that evidence. Okay? Now, in some systems, some countries, not all countries, at the beginning of the trial, the person is presumed not guilty. Okay? So, everyone is innocent. We say people are innocent until they're proved guilty. That's kind of an important concept in law. Okay? People are assumed to be innocent. So you can't just lock them up unless you have some pretty strong evidence at first, right? So they're assumed to be innocent. They're presumed to be not guilty. Then the prosecutor's efforts, I guess that's the state, the government, are to prove that that person has committed the crime and hence is guilty. Now, if it's not a crime, if it's a crime against another person, yeah, I guess so, yeah, and hence is guilty, okay? In statistics, the statement, the person is not guilty, is called the null hypothesis. So what's the null hypothesis here? The person is not guilty. That's called the null hypothesis. How about in terms of the can? What do you think the null hypothesis might be? So that's the one we're testing. And it's a little bit arbitrary, at least it seems to me, a little bit arbitrary which one you call the null hypothesis and which one you call the regular one, the other one. But, so like here, there's two possibilities, but anyway, they say the person is not guilty is called what? The null hypothesis. That's the one we're going to test, but that's also the one that we're going to assume is true first, and then test it. Okay, so the null hypothesis is the one that you assume is true, and then test it. Now, honestly, this kind of thinking really annoys me. If I was a student and had to listen to this, I wouldn't want to hear it. It's not, I don't know, my mind doesn't want to think about these these things in this way. But I had to do it, and you have to do it too. So anyway, the person is not guilty is called the null hypothesis. That's the thing we're going to test. So in the case of the other one, in the case of the soda cans, what is the null hypothesis? Because we said there's like two possibilities, right? But which one is the null hypothesis? Which is the one that we assume is true at first? We don't assume that the company is cheating at first, right? So which one is true at first? That the average is 12 ounces, right? That's the null hypothesis, that the average is 12, okay? So in statistics, the person is not guilty is called the null hypothesis. The person is guilty is called the alternative hypothesis, okay? So we have the null hypothesis, the person is guilty, versus what they call the alternative hypothesis, which is the person is guilty. Okay, does that make sense? So how about in the case of the soda cans, how should we set this up? The null hypothesis again is what? The average of the population is 12 ounces or more. We're not assuming the company is cheating. We have to prove that they're cheating. And the alternative hypothesis is? The average is less than 12. They are cheating, right? Okay, good. So, and then we use a notation for the null hypothesis, and in a notation for the alternative hypothesis, we denote the null hypothesis like this, and that's usually read null hypothesis, or H sub 0. And this one denotes the alternative hypothesis, that could be read as the alternative hypothesis, or H sub 1. Okay? So that they just stand for those two, the null and the alternative hypothesis. So which one do we assume is true at the beginning? The null one, which is denoted as H sub 0. Okay, so we assume that one. Okay? The null, in the beginning of the trial, it is assumed that the person is not guilty, right? We assume they're not guilty. The null hypothesis is usually the hypothesis that is assumed to be true to begin with, okay? The two hypotheses for the court cases, for the court case are written as follows. Notice the colon after these, okay? Notice the colon there. So the null hypothesis, H sub 0, notice the colon. The person is not guilty. Alternative hypothesis, H sub 1, person is guilty. Okay, is this clear? Okay. In a statistics example, the null hypothesis states that a given claim or statement about a what? A population parameter is true. Reconsider the example of the soft drink company's claim that on average its cans contain 12 ounces of soda. In reality, this claim may or may not be true. However, we will initially assume that the company's claim is true. That is, that the company is not guilty of cheating and lying. To test the claim of the soft drink company, the null hypothesis will be that the company's claim is true. Okay? So now, they say, let mu be the mean amount of soda in all cans, right? Why do we use a Greek letter here? Because they said it's the mean amount of soda in all cans. Okay? The company's claim will be true if mu equals 12. Thus, the null hypothesis could be written like this, right? Okay, so H sub 0 could be written as mu equals 12. Okay, is that clear? Okay. In this example, the null hypothesis can also be written like this, right? Because if we'd be happy if there was more than 12 as well, right? So it's could write it like this. Becomes the claim that the company will still be true if the can contains on average more than 12 ounces of soda. The company will be accused of cheating the public only if cans contain on average less than 12. However, it will not affect the test whether we use equals or greater than or equal in the null hypothesis, as long as the alternative hypothesis has a less than sign. Remember that in the null hypothesis and in the alternative hypothesis also, both of them, we use the population parameter in the statement, right? For example, mu, or what do they mean by P again? P? What proportion? Right, we didn't really cover that, but that's what he covered it so he's mentioning it here. And not the sample statistics such as X bar. So we don't use X bar when we describe the null hypothesis, okay? Or when we state the null hypothesis, and we don't use p hat. Okay, any questions about this? Okay. So definition, null hypothesis. A null hypothesis is a claim. So we had 3 examples so far. They're all claims, right? First one was that the person is innocent. Actually, the first one was that the soda cans are at least 12 ounces, the average of the population. The second one is that the person is innocent. The third one is that, what was the third one? Oh, about AP students? Okay. So we had 3. A null hypothesis is a claim or a statement about a population parameter that is assumed to be true until it is proven or declared false. I guess declared false is better. Okay, the alternative, because I'm not sure we prove it. We don't necessarily, it's not really proving it, right? Just because I collect a sample and the sample is really far away from the claim doesn't mean I really proved that it was false, right? But we declare it false. Okay? The alternative hypothesis in our statement, in our statistics example, will be that the company's claim is false and its soft drinks cans contain on average less than 12 ounces, that is, mu is less than 12 ounces, the alternative hypothesis will be written like this. Okay. So an alternative hypothesis is a claim about a population parameter that will be true if the null hypothesis is false. Okay? Everyone get this language? Okay? Let us return to the example of the court trial. The trial begins with the assumption that the null hypothesis is true, that the person is not guilty. The prosecutor assembles all the possible evidence and presents it to the court to prove that the null hypothesis is false. What's the null hypothesis? That they're not guilty. They want to prove that that's false. And that the alternative hypothesis is true, that the person is guilty. In the case of our statistics example, the information obtained from a sample will be used as evidence to decide whether or not the claim of the company is true. In the court case, the decision made by the judge or jury depends on the amount of evidence presented by the prosecutor. At the end of the trial, the judge or jury will consider whether or not the evidence presented by the prosecutor is sufficient to declare the person guilty. The amount of evidence that will be considered to be sufficient to declare the person guilty depends on the discretion of the judge or jury. Does anybody know in the U.S. system of justice how, first of all, you always can get a jury if you want one. If you don't want, you can say, no, I don't want the jury to test me. I want the judge to make the decision. But you have the right to have a jury to make the decision if you're being tried in a criminal court. Okay? So, as far as I know. So, and how many people serve on a jury? Does anybody know that? I think it's 12? A jury trial or trial by jury is a legal proceeding in which a jury either makes a decision or makes findings of fact which then direct the action of a judge. It is distinguished from a bench trial in which a judge or panel of judges make all decisions. Jury trials are used in a significant share of serious criminal cases in almost all common law legal systems. I don't know what the common law legal system. And juries or lay judges have been incorporated into the legal systems of many civil law countries for criminal cases. Only the United States and Canada make routine use of jury trials in a wide variety of non-criminal cases. Other common law legal jurisdictions use jury trials only in a very select class of cases that make up a tiny share of the overall civil docket, e.g. defamation suits in England and Wales, while true civil jury trials are almost entirely absent elsewhere in the world. Some civil law jurisdictions do, however, have arbitrary panels. Okay, anyway, so the availability of a trial by jury in American jurisdictions varies. Because the United States system separated from that of the English at the time of the American Revolution, the types of proceedings that use juries depends on whether such cases are tried by jury under English common law at that time. Okay, anyway. So how many do they have? Oh look, the history goes back to Greece. And Rome, but I would like to know. Anyway, I think it's 12. Okay? So 12. No, I can't get back to that screen anymore. can't hear you. It's different? Yeah. Well, I think in the U.S., I'm talking about in the U.S., I think it's 12. But anyway, I think it's 12. But so remember we said that you're assumed to be innocent, right? And how much evidence do you have to provide, or how clear does it have to be that you're not innocent? How difficult does it have to, how clear does it have to be that you're not innocent to show that you're guilty in the U.S. system? Anyone know? That question's not very clear. I'm saying that you have to have 12 people. All 12 people have to agree that you're guilty in order for you to actually be said to be guilty and not innocent. So you're assumed to be innocent, and unless all 12 people say that you're guilty, if one person says that you're not, one person on the jury says that you're not, they throw the case out. So it's the assumption that you're innocent is very strong, and it takes a lot to prove that you're guilty. So everybody is assumed to be innocent. That's an important concept in law. Okay? So anyway, at the end of the trial, the judge or jury will consider whether, so it's the jury, okay. All right, now, but in statistics, of course, the situation's a little different, right? We're not talking about innocence and guilty. In figure 9.1, which represents the court case, oh, you're still doing the court case, the point marked 0 indicates that there is no evidence against the person being tried. So we have to present some, as the prosecution, the government has to pile up evidence to prove that you're guilty, okay? So if they just, this amount of evidence, it's not enough. If it's this amount of evidence, it's still not enough. If this amount of evidence, it's still not enough. Finally, at some point, there's enough evidence, and we say that we reject the null hypothesis. Again, what was the null hypothesis? That you're innocent. So finally, the prosecution puts in enough evidence so that finally we're in this region, and we can reject it. Okay? Does everyone understand what this picture is about? What this graph is about? Just saying that at some point we're going to say there's enough evidence to reject the null hypothesis. So this is called the rejection region, and this is called the non-rejection region. Okay, is that clear? Okay, so they say we have arbitrarily marked a point C on the horizontal axis. Let us assume that a judge or jury considers any amount of evidence to the right of the point C to be sufficient, and any amount of evidence to the left of the point C to be insufficient to declare the person guilty. Point C is called the critical value or critical point. So this, he's just trying to give us an intuitive idea based on a court case, but this is really for statistics that we're talking about it. So the critical point, okay, in statistics. If the amount of evidence presented by the prosecutor falls in the area to the left of the point C, the verdict will reflect that there is not enough evidence to declare the person guilty. Consequently, the accused person will be declared not guilty. In statistics, this decision is stated as do not reject H0. Remember, H0 is the null hypothesis, and if we don't have enough evidence, we won't reject it. So if the null hypothesis was that they were cheating, if we don't have enough evidence, we won't reject it. I'm sorry, what did I say? The null hypothesis is that they were not cheating. If we don't have enough evidence, we won't reject that hypothesis. Okay, so don't reject the null hypothesis. It is equivalent to saying that there is not enough evidence to declare the null hypothesis false. The area to the left of point C is called the non-rejection region. That is, this is the region where the null hypothesis is not rejected. However, if the amount of evidence falls in the area to the right of point C, the verdict will be that there is sufficient evidence to declare the person guilty. In statistics, this decision is stated as reject the null hypothesis, or reject H sub 0, or the null hypothesis is false. Rejecting H sub 0 is equivalent to saying that the alternative hypothesis is true. The area to the right of point C is called the rejection region. That is, this is the region where the null hypothesis is rejected. Okay? Any question about this? Okay, there are two types of errors. So, the person has not committed a crime, but is declared guilty. Right? They're actually innocent, but we make a mistake and declare them guilty. In the first case, the court has made an error by punishing an innocent person. In statistics, this kind of error is called a type 1 error, or an alpha error. Actually, I don't recall that. But in the second case, because the guilty person has been punished, in this case here, the court has made the correct decision. The second row, okay, so now we have this. So if we make this table, this is the actual situation. So what are the possibilities for the actual situation? The person is not guilty, and the person is guilty. And then this is the court's decision. What are the possibilities for that? The court says the person is not guilty, or the court says the person is guilty. Now, if the person is not guilty, in reality, and the court says the person is not guilty, then they made a correct decision, right? But if the person is guilty, and the court says they're not guilty, then they made an error. And that type of error is called a type 2 error. The type 1 error was what? If actually the person is not guilty, but we declare them, or the court declares them guilty. Okay, that's called a type 1 error. Okay, understand? Now, if we rephrase this in terms of null hypothesis, then what is a type 1 error? If we rephrase this in terms of null hypothesis, then what is a type 1 error? Remember, the null hypothesis is what? The person is not guilty. So if the null hypothesis is true, but we say it's false, then we've made a type 1 error. On the other hand, if the null hypothesis is what? False, but we say that it's true, then we've made a type 2 error. So, what's a type 1 error again? If the null hypothesis is true, but we say it's not true. Okay, so that's type 1. Null hypothesis true, we say not true. Again, what's the null hypothesis? What's the type 1 error? Which one is the type 1 error? Null hypothesis true, but we say not true. That's an error, right? We made a mistake. It's actually true, but we said it wasn't true. One more time. What's the type 1 error? Remember, the person is not guilty is usually what we call the what? The null hypothesis. This is the actual situation. The actual situation, not what the court decides. The court can make a mistake, but the reality is, the actual situation is what? This one. So they're not guilty, but the court says they are. That's an error. It's called a type 1 error. In terms of null hypothesis, how does it work? This is the null hypothesis. So the type 1 error is what? Say it. The null hypothesis is actually true, but our evidence says that it's not true. Okay, that's type 1. What's type 2? The null hypothesis is actually not true, but we say it is true because of the evidence, of the random evidence that we've got. Okay, do you get it? Kind of confusing, right? But that's the language that they use.
We say this one.
Yeah.
False positive.
False positive? Oh, don't make me think like that. What? False positive, false negative. Okay, let's see, what is that? That's right, you're right. So, which is which? Let's see, the type 1 is one. I don't want to think about that. But it's related. Yeah. You could probably say something like that. In our statistics example, a type 1 error will occur when H0 is actually true, the null hypothesis is actually true, that is, cans do contain on average 12 ounces of soda, but it just happens that we draw a sample with a mean that is much less than 12, and we wrongfully reject the null hypothesis, H0. The value of alpha, called the significance level of the test, represents the probability of making a type 1 error. In other words, alpha is the probability of rejecting the null hypothesis, H0, when in fact it is true. So we'll see that more clearly in a few minutes. Because we're going to decide how far away we need to be in order to reject the null hypothesis. And when we make that decision about our criteria for how far away we have to be, that will imply a certain error level. Okay? All right. Let's rephrase it now in terms of probability. What is a type 1 error? A type 1 error occurs when a true null hypothesis is rejected. The value of alpha represents the probability of committing this type of error. That is, alpha equals the probability that H0 is rejected when in fact H0 is true. Okay, you understand what alpha is? So remember, this notation means conditional probability, right? So it says the probability that it says that given that H0 is actually true, we reject it. So even though it's true, we reject it. The probability of that happening is called alpha, and that's called the significance level of the hypothesis test. Okay, let's see. The size of the rejection region in a statistics problem of a test of hypothesis depends on the value assigned to alpha. Remember, the size of the rejection region. So the size of this and the size of this depends on alpha. In one approach to a test of hypothesis, we assign a value to alpha before making the test. Although any value can be assigned to alpha, the commonly used values are this, or this, or this, or this. In other words, this is like a 99% confidence interval. This is like a 95% confidence interval. This is like a, this is like a 97.5 confidence interval. This is like a 95% confidence interval, and this is like a 90% confidence interval. Usually the value assigned to alpha does not exceed. So we decide, do we want to have a 90% confidence interval? Do we want to have a 95% confidence interval? Do we want to have a 99% confidence interval? So we decide that at the beginning. You'll see what I mean by that in a minute. Now suppose that in the court trial case, the person is declared not guilty at the end of the trial. Such a verdict does not indicate that the person has indeed not committed the crime, right? Just because we say they're not guilty doesn't mean that they're actually not guilty. It's possible that the person is guilty, but there is not enough evidence to prove the guilt. Consequently, in this situation, there are again two possibilities. Now, I want to tell you an interesting fact. I don't know what you think about this, but if I ask the next question in the United States, I'll get one answer, and if I ask it at APU, inevitably I get a different answer. I'm sure that if I ask you guys this question, you're not going to give me the answer that I would get when I've asked it in the US. So here's the question. Which is worse, to convict an innocent person or to let a guilty person go free? Which is worse, to convict an innocent person or to let, so should we make a system where there's always going to be some errors, right? We're always going to make some errors. So we want to tune a system so that we make less of one type of error, and then we're going to make more of the other type of error, right? So we're going to be more strict in one sense. That means the other sense we're going to make more errors, right? So we're going to make errors. So which is worse, to make errors of convicting a guilty person or letting innocent people go free? Okay, how many people think convicting guilty person is worse than letting innocent person go free? Raise your hand. Okay, how many people think that letting an innocent person go free is worse than convicting a guilty person? Was that the same thing? Okay, hold on, let me say that. I'm sorry, probably made a mistake. All right, again, if you think this is worse, let me know. Raise your hand. Convicting an innocent person. 1, 2, 3, 4. Okay. Now, if you think this is worse, let me know. Letting a guilty person go free. Okay, it's unusual. It's almost half and half. Actually, every other time I've asked the question at APU, it's been like 99%. People say the worst one is letting an innocent person go free. Letting a guilty person go free. Sorry, I can't speak English. Letting a guilty person go free is worse. Okay? And usually, almost everybody says that. But if I ask the question in the US, it's the opposite. So I used to, but here it was actually closer to, more people said that it's worse to convict a guilty person. Maybe, anyway, but still there were other people that didn't think so. So that's just a cultural difference, I guess, right? Something different there. But anyway, going back to this. Now suppose that the court trial case, the person is declared not guilty at the end of the trial. Such a verdict does not indicate that the person has indeed not committed the crime. It's possible that the person is guilty, but there is not enough evidence to prove the guilt. Consequently, in this situation, there are again two possibilities. The person has not committed the crime and is declared guilty. The person has committed the crime, but because of lack of, okay, so in the first case, the court's decision is correct. In the second, okay, this is type 2 error. Okay, so there's a probability of making a type 2 error, and that's called beta. So what does that mean? That H0 is actually false, but we declare it to be true. Okay, that's called beta. That's called a type 2 error. Okay? So, all right, so we have this. let's take a little break, and then we'll go to this, the tails of a test, and a two-tailed test. Left tail, right tail. Okay. So we'll probably only get through section 9.1 today, but it's a little bit, it's kind of complicated, so I'm spending time on it. So now there's one more topic, and that's called the tails of a test. The statistical hypothesis testing procedure is similar to the trial of a person in court, but with two major differences. The first major difference is that in a statistical test of hypothesis, the partition of the total region into rejection and non-rejection regions is not arbitrary. So remember we had this picture. And here, it's kind of arbitrary where we're going to reject and where we're not going to reject. Where the court is going to reject and where it's not. The critical point is a little bit arbitrary. But they say in statistical example, it's not arbitrary. The partition of the total region into rejection and non-rejection regions is not arbitrary. Instead, it depends on the value assigned to alpha. As mentioned earlier, alpha is also called the significance level of the test. And also, what is alpha? This is alpha, right? It's given that this is true, the null hypothesis is true, that we reject it. That's an error, and the probability of that is called alpha. So they're saying that this C will depend on what we decide to make alpha. So if we decide, let's think about that. If we decide to make alpha really small, like only 1% chance that we'll make a mistake, then where does C? Does C move to the right or the left? Okay, as C moves to the right, alpha is smaller because alpha means the chance that we'll reject something, the null hypothesis, when it's true, and the rejection region is very small here, the chances of rejecting are smaller. Okay. The second major difference relates to the rejection region. In the court case, the rejection region is on the right side of the critical point, as shown in figure 9.1. However, in statistics, the rejection region for a hypothesis test can be on both sides, with the non-rejection region in the middle, or it can be on the left side or the right side of the non-rejection region. These possibilities are explained in the next three parts of this section. A test with two rejection regions is called a two-tailed test, and a test with one rejection region is called a one-tailed test. The one-tailed test is called a left-tailed test if the rejection region is in the left tail of the distribution curve, and it is called a right-tailed test if the rejection region is in the right tail of the distribution curve. Okay, let's see what they mean. Tails of the test. A two-tailed test has a rejection region in both tails. A left-tailed test has a rejection region on the left tail. Okay, let's see what they mean. So what they're talking about is this picture. So this is for what? 18 is what? Okay. The mean weight of backpacks for sixth graders in New York. Okay? The mean weight. So this is 18.4 pounds, which is how many kilograms? About eight or 9 kilograms. Okay, so the mean weight is this. So that's our claim. That's the null hypothesis. Now, when are we going to reject that? How about if we get something here in our sample? Maybe, maybe not. How about if we get something here in our sample? Maybe, maybe not. is the further we get away from 18.4 in our sample, the more likely we are to reject it, right? The null hypothesis, right? So what they're saying is it could be really high or it could be really low, and we'll reject the claim. And that's different than the soda can case. In the soda can case, if we got something which was really high, would we reject the company's claim? In the soda can case. If we got the average of our sample was 13 ounces, would we reject their claim? That it was 12 or more? No. So there, we don't have a rejection region on the right-hand side. We only have a rejection region on the left side. So what kind of test is that called? One-tailed or two-tailed? One-tailed, right? Whereas here, we might say, if it's really high or if it's really low, we're going to reject this claim. Okay? So that's called what kind of test? A two-tailed test. Okay, so some questions result in a one-tailed test, and some questions result in a two-tailed test. It's really just up to how you phrase your question, your initial question. Okay? So here's the here's the null hypothesis, what? Mu equals 18.4. The mean weight of backpacks for 6th graders in New York has not changed. It's equal to 18.4. Versus mu is not equal to, notice it doesn't say less than, and it doesn't say greater than, like we had in the soda case. It says not equal to. So when you have not equal to, that implies a two-tailed test. Okay, when you say not equal to, that implies a two-tailed test. When you say less than, that implies, for the alternative hypothesis, that implies a one-tailed test, or greater than, that also implies a one-tailed test. Okay, does everyone understand? Okay. This example was about Consumer Reports magazine conducted in 2008. A sample of 6th graders selected from New York schools showed that their backpacks weighed on average 18.4 pounds. Another magazine wants to check whether or not this mean has changed since the survey. The key word here is changed. In other words, it's not whether it's gotten lighter, and it's not whether it's gotten heavier, it's just whether it's changed. So that means two-tailed test, right? The mean weight of backpacks for 6th graders in New York has changed if it has either increased or decreased. This is an example of a two-tailed test. Let mu be the weight of backpacks for current 6th graders in New York. The two possible decisions are the mean weight has not changed, it's still equal to 18.4, or it has changed, it's not equal to 18.4 anymore. Okay? Anybody have any questions about that? Okay, so we get this test. On the other hand, here's an example of a left-tailed test. Reconsider the example of mean amount of soda in all soft drink cans. So we already did this. So this is what kind of test? Is this a two-tailed test or a one-tailed test? We're only interested in whether mu is less than 12 or not whether it's greater than 12. So is it two-tailed or one-tailed? It's one-tailed. This is the rejection region. The rejection region is only in one tail of this curve. Only when we get down here will we reject. Now what is this picture, by the way? What is this picture? What? The distribution of x bar, right? So what are we saying? I know that x bar floats around all over the place, right? At random, because I'm taking random samples. So I'll get x bar here sometimes, I'll get x bar here sometime. But if mu is actually 12, how likely is it that I'm going to get x bar way down here? Not likely. So if I get an x bar way down here, we say I'm in the rejection region, it's far enough away that I can assume that mu wasn't actually 12. Okay, that's the logic here. Now, how far away should we choose before we create the rejection region? How far away should we choose? Well, it depends on how much error we're willing to accept in our process. If we're willing to accept 5% error, then we should set it so that C makes 5%, this area equal to 5%. If we're only willing to accept 1% error, then we should set C down here so that this area is only 1%. So in other words, if C is down here, the rejection region is smaller, right? If C is down here, the rejection region is smaller, so we're going to, it's less likely that we're going to reject, and the possibility of making a mistake is going to be smaller, because it's less likely that we're going to reject. Okay? So that's the relationship between alpha and C. Okay, what's the relationship between alpha and C? If I set alpha smaller, that is the probability of making a type 1 error, if I make it smaller, that means C will move down to the left further. Okay? Now how about what happens if it's a two-tailed test? Suppose alpha is equal to 5%. Then C will be at a certain place, right? Now suppose this was a two-tailed test, and I still had alpha at 5%. What's going to happen to C? Where's C going to be now if it's a two-tailed test? Okay, so if we set alpha equal to 5%, C is here. That's for this one-tailed test. But what if it was actually a two-tailed test and alpha was equal to 5%? Then what? Then we have this picture. Alpha is equal to 5% means this area should be alpha over 2, and this area should be alpha over 2, or 5% over 2, and this area should be 5% over 2, so that the total error region is still only 5%. So what happens to C? It's going to have to move down, and this C is going to move up, is going to be up here. Okay? Does that make sense? Okay? So, okay. And now they talk about some examples here. So we should do one of these at least. Okay, so let's try this. A right-tailed test. To illustrate the third case, according to www.citydata.com, citydata.com. Let's look at my hometown. Boring place, but Philadelphia. What's that? What happened? Okay, let's look at another city. Or let's do this. Let's look at Seattle. Oh, let's look at this. My pen is moving here. Let's see what this is. What's going on here? I don't get it. How does this work? Click on this and it goes to this. Oh, here it is. Okay, so what do they tell us? Population in 2002, 82,000 people, not too many. That's what, about the size of Beppu? Beppu about 100,000 people, I think. So this city is about the same. Mean prices, all housing. Okay. All right, so, okay, to illustrate the third case, according to this database, the average price of homes in West Orange, New Jersey, which is close to my home, where I was born, was this price, $461,000 in 2007. Suppose a real estate researcher wants to check whether the current mean price of homes in this town is higher than this. So is this going to be a one-tailed test or a two-tailed test? One-tailed or two-tailed? One-tailed. And what's the null hypothesis? What's the null hypothesis? That the price is 461 or less, right? It's still 461 or less. And what's the alternative hypothesis? That it's more than 461, right? Okay? Okay, now what else can we ask about this? Okay, so where is the rejection region going to be? Is it going to be on the right tail or the left tail? Because he already said it's a one-tailed test. So is the rejection region going to be on the right side or the left side? The right tail or the left tail? The null hypothesis is that it's still 461, or we could say it's 461 or less. So that's the null hypothesis. When do we reject it? If we get something high or something low? High. So the rejection region is on the right side or the left side? Right side. So this is called a right-tailed test or a left-tailed test? Right-tailed test. Okay, good. Okay, the key phrase in this case is higher than. Is it higher than? Which indicates a right-tailed test. So if this is what you were trying to test, is it higher than? Then you're going to do a right-tailed test. Now you don't have to test that. You can test just, did it change? Maybe that's all you want to know. You just want to know whether it changed or not whether it got higher. If that's what you're interested in, then you shouldn't do a right-tailed test. You should do a two-tailed test. Okay? But if you're interested in whether it got higher, then you should do a one-tailed test, a right-tailed test. Okay? Let mu be the current mean price of homes in this town. The two possible decisions are as follows. The current mean price of homes in this town is not higher, so it's still the same. Or two, the current mean price of homes in this town is higher. Okay? Okay. We write the null hypothesis like this. It's equal to that versus it's greater than that. Or this could be, by the way, less than or equal to that. But this one has to be greater than or equal. Greater than, sorry. Right? Okay? Notice that here we can also write the null hypothesis like this, which, okay. Again, the results of the test will not be affected by whether we use, okay, where is it then? So here's the picture, right? If we get something up here, we're going to reject it. And this is a one-tailed, right-tailed test. When the alternative hypothesis has a greater than sign, it's always right-tailed. So when the alternative hypothesis has a greater than sign, then it's right-tailed. Okay? The area of this rejection region is equal to alpha, the significance level. So we decide how much error we're willing to make. Are we only willing to make 5% error? Then alpha, this area should only be 5%. That means the C should be somewhere. If we're only willing to make 1% error, then C is going to be up here. So we won't be able to reject this claim unless we get something beyond that. Okay? Again, assuming H0 is true, remember we always assume that H0 is true, the sampling distribution of X bar has a mean equal to this. So remember that. So, in other words, where do we locate this curve? That's kind of confusing because we don't know if this is true, right? So we don't know where to draw this normal curve. But remember, we're always assuming that H0 is true. So we're assuming in this case that mu is somewhere. In fact, we're assuming that mu is here. So we do know where to draw it based on that assumption. So based on that assumption, we draw the curve, we put mu here and the curve here. Okay? So it's all based on that assumption. We can't draw this curve unless we have an assumption like that. We will reject the assumption if we get something way up here. Okay? How will reject H0? We will reject H0 if the value of X bar obtained from our sample falls in the rejection region, otherwise we won't. Okay, so we have this, the signs of H0 and H1, and the tails of the test. Okay, now one more thing here, quickly. We will use two procedures to make tests of hypothesis. The p-value approach and the critical value approach. So the p-value means that, okay, we've been talking about the critical value approach so far, which means we set a critical value. How do we get this C? How do we decide where C is going to be? We decide how much error we're willing to accept in our decision-making process. And that determines how much green area there should be, and that determines where C should be. So that's one approach. Now there's another approach, and that's called the p-value approach. Now the p-value means we get a particular X bar, right? Suppose X bar turns out to be right here. The p-value for that value of X bar means the area to the right of that X bar. So if I get this X bar, maybe there's 5% area to the left, that would mean the p-value for what I got was 5%. Or maybe it's just 4%, then the p-value is 4%. Or maybe it's just 1%, then the p-value for the X bar. So if the p-value is small, what does that mean about rejecting? That's the last question. If the p-value is small, what does it mean about whether we should accept or reject? So the p-value is small means the area to the right is very small. What does that mean about whether we should reject or not? We should reject, right? Now, we don't have a rejection region in that method. We just say, we got a very small p-value. It was just 1% to the right of the X bar that I got. Therefore, should I accept the claim or reject it? I should reject it. Okay, that's the idea of using the p-value. You don't have a so-called critical region. You don't decide at the beginning, I'm going to accept if it's less than 5%, if it's more than 5%, and so on. You don't do that. You just check the p-value, just check the area to the right of X bar, and based on that, you decide whether you should reject or accept. Okay, so that's the idea. Okay, so you're going to have some homework in this section. It's going to be due for next week. Okay, so I spent a lot of time on this. It's long and kind of tedious, but if you want to get used to the language that they always use, you have to understand this section. Okay, so we spent a lot of time on the language that they use. It's nothing, really, we didn't do any new statistics here, right? We didn't learn anything. We just learned language, right? The language of what's the null hypothesis, what's the alternative hypothesis, what do we mean by a rejection region, and so on. It's just kind of language, okay? But in order to understand what people are talking about, you need to know this language, okay?